So yes, I'm Damien Moal from Western Digital. The presentation is about work we've been doing on NVMe PCI Endpoint function driver, and we're working on this together with Niklas. So, quick outline, I'll give some background why we're working on this, describe a little bit what the PCI endpoint subsystem is in the kernel, go through our NVMe endpoint function driver, showing the design and some performance result we got, and status and next step to conclude. So, why this work? Some background. So, well, if you're working for a hardware vendor, you sometimes have to think about changes to standards like NVMe, new command set, new features, and you want to be able to evaluate beforehand before you go and start making products with that, or even trying to push these changes to standard committees. You want to be able to quickly evaluate the benefits or verify that you are actually getting benefits from what you're trying to do. Problem is that an NVMe controller, most of the time, due to performance constraint, they are all very often completely implemented in the hardware. Most of it, only a few things are actually firmware in those devices. And so if you have to wait a few months or even more, a few years for the next iteration of a controller SoC to do your test, well, you cannot really quickly check your work. So in that context, software-based platform to prototype things and verify changes is very much desired to be able to quickly iterate through changes and fine-tuning your specification change. So what you can do, what you can use today for a software implementation. So the kernel supports, for example, NVMe Fabrics, which is essentially a software implementation of an NVMe controller. You have the host side and target side in NVMe Fabric, and the host side is essentially an NVMe controller implemented in software. So you can change this, tweak this, support new commands, new features, whatever you want to test. So change essentially the kernel driver to support that and do your test with this. However, doing that, you lock yourself into the requirement that whatever host you're using, it has to support NVMe over Fabrics. For example, to connect using NVMe TCP to your actual device implementing that feature. And that's fine in some cases, but not always, especially, for example, if you're working with a BIOS or a bootloader, and the feature you're trying to test, to evaluate, has to be used by these very low-level software pieces that generally do not support such complex things as NVMe Fabrics. The other software solution that you can use is QEMU NVMe emulation device, which is also 100% software. But again, you lock yourself into a very specific set of hosts, which is that now you have to run inside a VM. So if your BIOS or your bootloader, it depends on some special hardware, you cannot run that there. Not necessarily. There are, of course, ways to do that, but that's more work. But hopefully, we have this thing in the kernel, the PCI endpoint subsystem, which allows you to actually create PCI devices in software. So what is this subsystem? Essentially, there are two parts to it. One is a set of, it's kind of two sets of APIs, generic APIs. One to write endpoint controller drivers, and the other side of this is endpoint function drivers, which plug into the controller driver to create a PCI endpoint. The controller API essentially deals with all the things that a host sees over PCI, so PCI bars, the configuration space, interrupt control, because you now are an endpoint, so you raise interrupt to your host, and you also need to deal with data transfer between your endpoint and your host, so there is API for that, either MMIO or DMA. And the function driver goes on top of that, and we'll deal with the actual function that will be exposed through the PCI configuration space to the host. So device type configuration, event notification to the driver about the link state, the link with the host, the state of the link with the host. There is API also for raising interrupt, for doing PCI address mapping so that you can transfer data between the host and your driver. So this is all upstream. It's been upstream for a while. And there are quite a few controllers that are already supported that can generally both work in root complex or endpoint mode from different vendors. So one of these is the PCI ROC chip, for example, which you can find on the Pine 64, the ROC Pro 64 board, which is very easy to procure, and there are others. For the function drivers, there's not a lot. There's one very useful, which is the test endpoint function. So it is an endpoint function driver that creates just a dummy device, which can be served on the host side by the counterpart driver that is also with the kernel, and that allows you to test data transfer between the host and the endpoint, as well as interrupts and bar accesses. There are also the non-transparent bridge endpoint function drivers, which are drivers that create devices that allows that creates essentially a PCI channel for communicating between a host and an endpoint. So it's just about data transfers. It's not really doing anything in itself with the data. And then there's the MHI endpoint function driver, which is for some Qualcomm hardware MHI bus modem drivers. There are patching being sent or discussion happening also on the list about VirtIO net function driver that some people want to implement. Okay, so now we have all this. We want to use this to create an NVMe function. What board do we want? Do we use? So what we were after when we started this is something that has decent performance, so at least PCI Gen 3. So meaning that a board that has that is capable of endpoint with a PCIe or M.2 connection. The ability to connect some peripheral to have backend storage for the NVMe controller, so either SATA or M.2, so that we can use SSDs, SATA SSDs or NVMe SSDs as backend. Ideally, good upstream Linux kernel support. You'll see that that did not happen, and we had to do a lot of work on that. Also easy to use, easy to procure, and cheap if possible, because of course there are, if you talk to hardware vendors, there are a lot of development kits or evaluation boards or SoC evaluation board that you can buy out there, multi-$1,000s, you need an NDA to get them, etc. We want something where we can cycle through more quickly, easier to procure so that more people can use it, etc. And yeah, in the end, we didn't find really anything that matched everything here that we wanted. So we went first with the easiest to get that had the best Linux support, but not really the best hardware, which is the Pine ROC Pro 64. You can see the PCI slot here that you can normally use to plug any PCI device and use with the board, but if you switch the PCI controller to endpoint mode, now it becomes, the entire board becomes an endpoint. So this is only PCI Gen 2. There's no extension for backend storage with SATA or M.2. There is, however, USB 3, so you can plug whatever storage through USB 3, so that's kind of a fallback here. And the support for this was upstream, but unfortunately it turned out that the endpoint side of it was extremely buggy. So we had to do a lot of debugging work to get that to work. And also there is no PCI DMA channel driver upstream, meaning that the only thing we can do is MMIO data transfer. So plus the fact that it's PCI Gen 2, it's extremely slow. but it's cheap and easy to procure, so we started with that. Hopefully, we got an update. Rockchip put out the RK3588 evolution of the 3399, which was the Rock Pro 64, with much better performance, better CPUs, PCI Gen 3, an additional M.2 E key for putting SSDs or SATA adapters there for our backend storage. But the counterpart was the upstream support was absolutely not mature, so we had to work on that and improving it. Niklas did a lot on that. But luckily, we already had the PCI DMA channel driver for it, so we knew that it was going to be much faster. Still, also easy to procure and cheap, so great to work with. Bonus is that like most of these controllers that can do endpoint, of course, it works also as a root complex. So you can use 2 boards, one as host and one as an endpoint, and you end up with a very compact test system, which is extremely convenient to just put that on your desk to do your testing. Of course, you can use as a host any normal PC, but why risk it, right? You'll see that there are gotchas to be aware of when you plug PCI cables like this from an endpoint board. Okay, so using this, actually, what I'm going to present here, the NVMe Endpoint function driver itself works as well on the Rock Pro 64 and the Rock 5B. And so what we did is, as usual, try to be lazy and not write a lot of code. So we decided to reuse the kernel NVMe stack. Essentially, we know what we have already an NVMe controller implementation in the kernel, which is done by the NVMe Fabrics code. So let's reuse that. And so essentially what we did is create that endpoint function driver to expose over PCI an NVMe host controller. That's all we do. We don't really touch anything about the NVMe commands. All that the function driver does is essentially create the I/O queues that we expose over PCIe that the host can then use to submit commands and get completions from. And the other thing that the driver does is managing the data transfers, because that's not done by the NVMe host controller. Well, it is done, but in a different manner, not explicitly through a PCI mapping that the host controller, Fabric host controller is not aware of. The other thing you'll notice here is that NVMe Fabric's host controller, you can have different targets, and your backend, it means that the backend storage for that NVMe function can be anything that the Fabrics controller supports. So if you want a local storage, you can use the NVMe loop target and either use files, regular files, that can be on the SD card for the board, or the eMMC storage, or SATA, or whatever you have plugged there. You can also use the network to go NVMe TCP to another machine. That also works perfectly well. Anything, again, that the Fabrics controller supports will be exposed through PCIe. That's what the function driver does. So if we look at how commands are executed, again, the driver itself, all it does is get commands, so through the queues that it created, and manage data transfer. So when if we look at the path of a command, we get the NVMe commands descriptor, the CDBs from the submission queues. We do very minimal parsing and checking of these commands. We need to look at the command still, because we need to be aware if it's a read or write to know when we have to do data transfer. Second thing we do is get the PRPs, which are the descriptor of the command buffers, so that we know where on the host over the PCI we have to access data or send back data. If we are dealing with a write command, we get the data that we have to write, so there is a data transfer here. Step 4, we execute the command. And to do that, we simply pass it to the kernel host fabric controller. It does its thing. It executes everything. And there is a callback that signals the completion, at which point, step 5, if it was a read command, we transfer the data back to the host and finish everything for that command by queuing the completion entry in the completion queue and raising an IRQ to signal the host the completion of the command. So very simple, because all the heavy lifting for the NVMe command parsing and execution is done here. This is all fairly simple, but you'll notice that the red boxes here are actually blocking operation because we do data transfer between the host and the endpoint. So we have to wait that this data transfer happen before we can go to the next step. So that was kind of challenging because if you do this in a single thread manner, you end up with an NVMe endpoint that will do QDEPs 1 per queue. That's it. And that's not really the NVMe model. So you want to be able to do something better than that. So and the other also kind of annoying thing with the endpoint infrastructure and endpoint controller in general is that you do not get an IRQ when the host writes to something to a bar. So in the case of NVMe, the head and tail doorbells for the submission and completion queues are in the bars. And when the host submits a command, it will write the tail of the submission queue doorbell, and you do not get an interrupt for knowing that happened. So what you have to do on the endpoint is constantly poll those doorbells to detect if the host sent new commands. So that means one more queue, one thread. Then we have our command execution, which has these red boxes that are blocking. And so to avoid blocking and be QDEPs 1 per queue, we decided, okay, let's execute each command in its own using a work structure. So essentially what we do is span works 1 per command so that we get parallelism of execution and we don't have to wait for completing one command before starting the next one. And again, each here thread will do the PRP transfer, data transfer, etc., and use the NVMe driver, kernel NVMe driver or host controller to execute the command. And the completion is also a thread in itself, but that's just an optimization so that we can do kind of a hierarchy folding so that we don't flood the host with one hierarchy per command. So we essentially aggregate completions in this thread, put everything in the completion queues, and raise a single MSI hierarchy for signaling a bunch of completions. There is also another thing, which is at the initialization of the driver itself, you have to wait for the link to come up so that you can properly manage the NVMe controller state registers over shown to the host. So there is another thread that actually does polling. You also must be ready in your function driver for the host suddenly shutting down. And that is something you can detect as well by looking at the controller status registers. So yeah, that's the overall design. Again, not really super complicated, just a bunch of works, and then you pass along a command to this different stage to process it. Most of the code end up being dealing with the PCI transfer and the mapping of the submission queues, completion queues, etc. For configuring this, it's actually very easy. Again, because we reuse the fabrics code, the NVMe fabrics code, how you configure your backend storage is essentially the same as how you configure a host and target a system with NVMe. So you can either use NVMe CLI restore with the configuration file for it, or directly write into config.fs, which is the example I have here. So first thing, for example, you tell the You create a namespace through config.fs, and then you tell that namespace, okay, you're going to be this device, which is in this case a SATA SSD I was using here. After that, you create your loop, so you essentially hook up that target with the controller through NVMe loop. You set up your vendor ID, device ID, the number of interrupts, and also the controller options, where you can specify things like, for example, the number of queues that you want to have for your Fabrics controller. Next, it's the PCI endpoint side, where you enable the function. You link it to the controller you want to use for that function. So there's only generally one on your on the board. And finally, you start the controller, which links everything together, and actually will do the connection between the host and target on the NVMe Fabric side, and also start the thread there, which will be polling the registers for the link state, and also the NVMe registers to wait for the host to tell you, I'm here and I'm starting to use use you. Example, an NVMe HDD. Why not? Because we can. You just need to connect an HDD over SATA and use that as a backend storage for your controller. So we had fun with that. All you need is actually an external. You cannot. An HDD needs 12 volt. There is no 12 volt on the ROG 5B, so you need an external power supply for that. But other than that, it's just as simple as connecting the drive and do the configuration like I just showed. Using a regular PC host, you can see, for example, here the BIOS starting and telling you, okay, I found this NVMe device, it's here. So you can see your NVMe HDD listed by the BIOS, and if you want, you can even boot from it if you install something on there. Okay, performance. What does that give us? So to avoid any limitation due to the backend storage performance itself, I did some measurement using NullBlock, meaning so NullBlock is simply a dummy block device that is not accessing any media. It's always completing read and write commands immediately. So it gives you a very simple way to measure the maximum performance you can get from this setup and from the endpoint function driver. And what we end up with using 8 IO queues for our Fabrics controller. So because there are 8 CPUs on the 8 cores on this board, so we just simply used 8 IO queues. For read commands, we can go up to 40K IOPS. Kilo IOPS, and up to 2.2 gigabyte per second transfer speed. So not bad, definitely not what you can get from any cheap consumer SSDs these days, but still, given that this is all implemented by software, not too bad. Write commands give you a little bit better IOPS, about the same maximum throughput. There is, however, something strange happening when you do sequential writes instead of random writes. Suddenly, the maximum throughput drops to 1.4 gigabyte per second instead of the maximum 2.2 that we can get for reads or random writes. No idea why. We're still looking into that. The other thing here to notice that we didn't see, except from some case like the random write here for 4K random write, the number of queues doesn't really improve performance. So the 2 bars, blue and orange here, are 1 or 4 IO queues on the PCI side, and it doesn't really change the performance. And the reason for that is that processing one queue in itself is very light in the endpoint function driver, and once we get command from there, I explained that we fork these work items so that the commands are executed on parallel on all available CPUs. So having more queues is not going to improve that. You will still be parallel. So most of the time you can already get the maximum performance even with a single queue pair on your endpoint function. There is one thing to notice here, though, is the QDEPS1 performance there. There are actually no bars, because for the scale of this thing, you can see them. What you get is 166 IOPS max. That's the best I could ever get. And why? Well, it's software. Everything shows up when your QDEPS1, all that chain of data transfer, PRP transfer, etc. You are directly measuring it, and it tells you that one command takes a second divided by what? A bit less than a millisecond. No, more than that, 10 milliseconds. A few milliseconds per command, essentially. So unless you go high QDEPS to get commands being processed in parallel, that's the performance you're going to get, which is, yeah, of course, not great. But yeah, it is what it is. It is software, so it's still easy to use. I don't think we can do much about that. Some tweaks might get us to 200 IOPS maybe, but that's pretty much it. I don't expect much improvement in that area. Okay, so status. So the ROC 5B implementation, easy to use, stable, but we had to do a lot of patching. I mean, Niklas did a lot. I did some as well. Performance overall, I'd say it's acceptable, except, of course, the QDEPS1 case. So if you have a latency-sensitive application that does a lot of QDEPS1 IOs, yeah, don't try to measure anything with that. That's not going to look great at all. But overall, I'd say it's like a low-end SSD-like performance. It's actually better than what you can get with a SATA SSD. So it's in between SATA and NVMe SSD performance, as long as you operate at high QDEPS. The only thing we are still chasing as a big problem is that when you connect this to an AMD machine as a host, so we've tried different Ryzen machine as well as EPYC machine, there is a problem, which is that the IOMMU tells you GMA timeouts. It just simply doesn't work. The IOMMU refuses to, something is going on. If you do the exact same setup on an Intel machine, it's going to work perfectly fine. But on AMD, there are problems with the IOMMU. And if you turn off the IOMMU, it works, but it's extremely slow. It's horribly slow. So Niklas actually looked into it a little bit, and I think it's related to the address translation services. We don't really know what's going wrong with that and why we see these IOMMU timeouts. So still under investigation. Next step. So as I said, lots of patching has been done. So we are going through that pile of patches and trying to upstream everything. So we have kind of three series that are in flight, and the fourth one is the NVMe Endpoint driver itself that we still need to send. So the first one is we did a lot of fixes to the PCI Endpoint's subsystem around the memory mapping API, because it turned out that this API, despite the goal of being controller independent, ended up actually exposing directly the constraint, the mapping alignment constraint of controllers to the endpoint functions, meaning that depending on the controller you were using, you had to do mapping differently, which was, of course, not acceptable. So we had to rework a little bit that API to hide that requirement and have a mapping functions that are a bit more intelligent, and end up with a common API for all functions. We also have another series that fixes the ROC Pro 64 controller, so the RK3399 SoC PCI controller, which is buggy. So both for the mapping API as well as how the controller is programmed. There are problems there. So if you read the TRM for that SoC, it's extremely unclear. But after a lot of digging, we figured out how it's supposed to be working, which is one of the reasons why we had to do the first series as well. So lots of fixes in that area as well. The newer RK3588 for the ROC 5B board doesn't have the endpoint driver for the PCI controller upstream. Niklas wrote it and is sent it already, I think. We just need the rebase for 6.10. So this is ongoing. And once we get all that, actually we don't even need the RK3588 endpoint driver. We can send the NVMe endpoint function driver upstream itself. We will need the PCI subsystem API changes though, because we depend on it. If you want to try this out, we have code out there on my GitHub. I have a full build tree that you can grab and just type make, and it will generate an image to put on the SD card of the board, and that will give you everything you need to run your endpoint. So one thing I wanted to add as a kind of a conclusion slide, because people always ask me, where do you get the PCI cable to connect the boards? Well, there's a vendor, very convenient, that has lots of different cables, including the RxTX cross cable that you need to connect the endpoint with a host. So I put the link here and the reference. There is one gotcha, however, you have to be very, very careful to not use that cable as is, because the cable has the power pins. So what happens is that if you plug that with the power pins still there, you turn on the ROC 5B board, the PC is going to start blinking up and the fan's spinning because the power goes there as well. And so you end up having a big PC drawing power from the small ROC 5B board. Yes, what can go wrong with that? So make sure to get a very sharp cutter knife and cut out the pins listed here, which are the 12 volt and 3.3 volt power pins. Leave the grounds, that's fine. You don't get any ground loop problems with that, but you have to cut the power pins, otherwise, yeah, things can get really funny. And that's it. Any question?
Gick ju nästan. Well, it's super interesting work that you are doing, so I'm very impressed. I was just thinking, like a few years back, there were this very interesting blog post of somebody who hacked into their hard drive and booted Linux on the hard drive. It was a Marvell shipped ARM dual core that they had in there.
Yes.
So with this endpoint framework and an MTD raw NAND controller and another endpoint controller in the hard drive, you could technically run a hard drive on Linux, right?
Well, again, I mean, this is Linux. I mean, yes, it's an NVMe endpoint, but this is Linux. So Linux is already running. I mean, you don't have to reinvent the wheel or hack that device. That's exactly why we're doing this, actually, to simplify that kind of hacking. Yes, I'm aware of the work you're mentioning. I was in the middle of it because we had that. It was actually, I don't know, George, can I say the name because it's so funny? They call that Red Hot instead of Red Hat. Just whatever, I mean, the fun code name we had. Yes, Linux running in the drive on spare cycles that the drive otherwise doesn't use. That was a thing. There was no real killer application for that. But if you think of these days computational namespace with NVMe, things like that, yes, and here you go. If you want to prototype something, you can do that. So actually, there is another person, if you look at the patches, who is always commenting on our patches, that is kind of working with us on this, who is, so we are more interested into the like kind of the NVMe standard work that we can do with this. But that person who is working for a university is more interested in exploring computational namespace. And so that kind of platform give them exactly that, a very easy to implement device that can do computational namespace. And so that is another possibility. Yes, Linux is running here, and then you can actually, even if you want to have your data passed on to applications, you just need to add an API for that. I mean, it's software. Just write it.
The application I had in mind was actually something new that came up, which is like nowadays some customers are very interested in following the bill of materials, let's say the trusted chain, and they don't want an alien firmware in their drive controller for military reasons. Performance doesn't matter. It's not a number of IOPS, etc. They are not caring about that. They are caring about controlling the software toolchain. So for them, running a Linux, which they have already certified, just with this endpoint controller on their drive towards a raw NAND flash, say there, that would be super interesting.
Not something I thought of, but yeah, definitely I think a valid use case, yes.
So I did poke Niklas on the shoulder here and ask, but what kind of hardware is in these Rockchip devices?
They actually have a lot of things.
So I'm thinking about the PCI Express controller and PHY and stuff like that. Do you know which IP?
So the controller is it's the Designware IP block.
Yeah.
So that's the Rock Pro has a Rockchip IP block for the controller, but the 3588 switched to a Designware IP block. So it's actually so you need some glue driver that is different from the other, but like it becomes part of one of these. I mean, very similar to these.
Yeah. Okay. Yeah.
I think it's made by Cadence. The one I think for the 3399, I think the controller is made by Cadence.
Yeah, the driver for the Rockchip and the Cadence, they look eerily very similar. So I'm pretty sure they are the same actually IP blocks, and there's one driver we could get rid of because they are essentially the same. Yes.
Yeah. And that also means that the DMA is the part of the Synopsys controller.
Yes,
that you use.
so that's why it was there already. It was there actually for the root complex mode, the regular mode, but it doesn't change for endpoint, so you just can reuse that.
Yeah.
Now, when you're looking into all those, have you been looking into the Jetson from NVIDIA also when you investigated, because they have a bit more performance, PCI Gen 4, and now they have the Jetpack 6 upstream?
Yes. I did look in all the boards that we could find that had endpoint, and Jetson was there, yes. Just more expensive, harder to procure, that's all.
Okay.
So we just went for the simplest one. The upstream support also not great. You have to use out-of-tree stuff, from what I remember. Maybe it improved, but at the time when we started that, more than a year ago, it was still a lot of out-of-tree things that we really wanted to avoid.
Yeah, I'm guessing also that's a PCI Gen 4 device, or something like that. And they
Renesas also is pushing PCI Gen 5 things.
Yeah, with those long cables, you are going to have problems.
But Renesas doesn't really have like a consumer board that you can buy easily. You have to buy the reference design, which is several expensive, and you need a contract, etc. So this one, we just went online and ordered a bunch of them for $200 a piece, and a week later we had them. So, and again, it's great because more people can try it out and play with that. So we really didn't want to focus on expensive hardware, even though we could. That's not what we wanted to do.
More questions? Yeah, one more.
It looks a bit like the Gadget FS regarding the PCI endpoint here. Are you seeing it going the same direction? So you have a lot of PCI devices you now can do in software in the future with your work here?
So the endpoint subsystem was already there. Again, there was some really serious problem with the mapping API, but it was there. So you can, today, if you want to write your own, yeah, go ahead. The harder part is really, can you find the hardware that matches what you want to do? So that's harder, but as for example, like the ROG 5B are already available now, it's way easier. We did not write the endpoint system itself. We are just patching it with for the bugs we found out doing this work. But yeah, it's again, as I mentioned, there's someone who wants to do VirtIO.net. There was a couple of months back someone who proposed some block device function driver. And everybody said, yeah, no, do either VirtIO or wait for the NVMe things. Don't do your own non-standard block device. But yeah, there is interest, and we see more and more proposal or discussion about new endpoints.
Anybody else? No? Well, thank
Okay.
you very much.
Thank you.